All right, so this is the plan for today. So from last time, there is a result which I could not prove. I will come back to this. This is a theorem of Serre, which identifies height 2 ideals so that R mod I is Gorenstein when R is a regular local ring. We will show this for dimension 2 regular local rings, and later on, when I discuss growth index definition using canonical modules, I will generalize it to any regular local ring. Okay. Then we begin our discussion on the other approach to Gorenstein rings by Hyman-Bass. So Hyman-Bass approached Gorenstein rings through rings and modules of finite injective dimension. So he studied when injective dimension is finite, how do we produce modules of finite injective dimension, how do we characterize the injective dimension through extension functors, and number of results about injective dimension. So we will characterize injective dimension in terms of supremum of x tie km r not equal to 0, where Rm is a Rm is a Noetherian local ring and M is a finite module. So look at all the x ties of k comma m and find the largest I so that this is not equal to 0. And if there is no such I, then injective dimension will be infinite. We will see a generalization of this formula. So this generalization brings in another module n, finitely generated module, so that depth of n plus supremum of I, x I and m is not equal to 0. That is always equal to injective dimension. So in some sense, this can be regarded as some sort of analog of the Oslander-Buxbaum formula. Oslander-Buxbaum formula related projective dimension and depth with the depth of the ring over which the modules are constructed. Okay, but here we have the ring in the background, and the depth of a arbitrary module is being related with the injective dimension of another module. Okay, so I will prove this. This is very important formula. For example, it will prove this part B will imply that the injective dimension of a finitely generated module over Noetherian local ring is always equal to depth of R. Okay. So this is very different behavior of injective dimension from projective dimension. Yeah, projective dimension can take any value uh, between 0 and depth of R, but injective dimension takes only one value, namely depth of R. Okay. Now there is a deep theorem due to several mathematicians which says that if there is a finitely generated module of finite injective dimension, then the ring is Cohen-Macaulay. So once you have a module of finite injective dimension, the ring will be Cohen-Macaulay, and therefore depth of R is dimension of R. So injective dimension has only one value, namely the dimension of R. But that is a deep theorem. We will not prove that. Okay. Yeah. So then we will also prove that the dimension of the module is a lower bound on injective dimension. Okay. So if you combine these two facts, now take m equal to R, then it says that the dimension of the local ring, okay, is equal to depth of the local ring. If R has finite injective dimension, then dimension of R is depth of R, and therefore R is Cohen-Macaulay. Okay. Yeah. So Hyman-Bass's definition of Gorenstein ring is these are local rings, Noetherian local rings which have finite injective dimension. Yeah. So last time I introduced the classical definition of Gorenstein rings. Remember the classical definition of Gorenstein rings. So Gorenstein rings classically are Cohen-Macaulay ring and any system of parameters generates an irreducible ideal. Yes. So so we need to the Bass's definition should imply this definition, that if a local Noetherian ring has finite injective dimension, it should be Cohen-Macaulay, and every system of parameters must generate an irreducible ideal. We will prove that. Okay, so these two definitions are equivalent. Yeah, these two definitions, classical definition and Hyman-Bass definition, they are equivalent, and finally the equivalence will be shown with the Grothendieck's definition through canonical module. Okay, so this is the plan for today, and so let us begin. Are there any questions? Is the handwriting readable or is it too small? Has everyone gone to sleep?
Okay.
It's readable, sir.
Okay.
Yeah. Okay. All right. So let me begin by proving Sayre's theorem about Gorenstein rings. As I said, I will prove only a special case. Let Rm be a two-dimensional regular local ring, and I an M primary ideal. So it's a height 2 ideal. The general theorem of Sayre is about height 2 ideals in any regular local ring when the quotient ring is Gorenstein. So this says if you have two-dimensional regular local ring, I is an M primary ideal, then R mod I is Gorenstein if and only if I is a complete intersection, which means I is generated by as many elements as its height. Okay. So to prove this, I need a lemma about Betti numbers in a free resolution. So let R be a Noetherian domain. And M a torsion module, torsion finite R module, having the following free resolution. Uh, 0 to R Bn R Bn minus 1 R B0 to M to 0. Okay. So suppose I have this free resolution. I'm not saying it is minimal. I just have some free resolution. I know the Betti numbers, and M is finite and torsion free. Then the alternating sum, take the alternating sum of the Betti numbers. This is 0. So let Q be the quotient field quotient field of R. I have a Noetherian domain, and Q is the quotient field of R. Then M is torsion. M is torsion module, torsion R module. So that means if I tensor M with Q over R, this is 0. So tensor the free resolution with Q, then I get 0 to Q Bn to Q Bn minus 1 to Q B0, and when I tensor M with Q, that becomes 0. Okay. So tensoring with Q means I am localizing at non-zero elements of R, and localization converts exact sequence into exact sequence. So this is an exact sequence of Q vector spaces. Exact sequence of Q vector spaces. These are all finite dimensional. So by generalized rank nullity theorem, the alternating sum of their dimensions is 0. Yeah, is this clear? Any doubts on this lemma?
Fine.
Okay, so let us now prove Serre's theorem. Now recall what I proved last time. Recall that if Rm is a regular local ring and R mod I is an ideal, and R mod I has a free resolution, free minimal resolution, uh, 0 to R Bn minus 1, R B1 to R mod I to 0. Then R mod I is Gorenstein. Does anybody remember what is the criterion?
DA2 has dimension 1.
The last Betti number is 1.
Yes.
Yeah, the last Betti number is 1. Okay, so we just apply this criterion. Now our dimension is 2 and I is M primary. So I is M primary, and therefore R mod I is Artinian, and therefore its depth is 0. Now, so apply Oslinder-Buxbaum formula. Oslinder-Buxbaum formula says projective dimension as an R module plus depth of R mod I as an R module is equal to depth of R. But depth of R is 2 because R is a 2-dimensional regular local ring, that is Cohen-Macaulay. Depth of R mod I is 0, and therefore projective dimension is 2. Projective dimension of R mod I is 2. So therefore, R mod I has a free resolution. R mod I has a minimal free resolution of length 2. It has a minimal free resolution of length 2. So write this minimal free resolution RB2, RB1, okay, then R mod I to 0. In a minimal free resolution, what is B1? What is B1? Can anybody tell me what is B1?
Mu of I.
Number of generators of I, right? Because R to R mod I has kernel I, and then I will map a free module of rank equal to minimum number of generators of I. So B1 is mu I, and mu I is M primary ideal. I want to determine what is mu I. Okay, so we want to know this B1, but B2 is under control of because of Gorenstein property. So R mod I is Gorenstein. R mod I is Gorenstein. If and only if B2 is 1. Okay, but B2 minus B1 plus 1, that is 0. Okay, and B1 is mu I. So B2 plus 1 equal to mu I, and therefore B2 is 1 if and only if mu I is 2. Yeah, that's Serre's theorem. That you take two-dimensional regular local ring, take any M primary ideal, then R mod I is Gorenstein if and only if mu I is 2. So by using this, you can write examples of many non-Gorenstein rings. Okay, if I is generated by two elements, then it's a system of parameters. Any system parameters in a Cohen-Macaulay ring is a regular sequence. And if I is generated by two elements, then because it is a regular sequence, Koszul complex gives minimal free resolution. Yeah, converse is we have already seen many times. The converse, that if mu I is 2, let us say I is generated by AB, then AB is a regular sequence because the ring is Cohen-Macaulay and AB is a system of parameters. So AB is a regular sequence. So the Koszul complex of these two elements, okay, that gives a minimal free resolution. This is a minimal free resolution. And therefore, B2 is 1. Yeah. So R mod I is Gorenstein. Yeah, is this clear to everyone? Any questions in Serre's theorem? So whenever I is M primary, R mod I is always Cohen-Macaulay because dimension of R is 2 and R mod I becomes Artinian. Artinian rings are Cohen-Macaulay, but they may not be Gorenstein always. As soon as you pick I to be 2 generated M primary ideal, then and only then R mod I is Gorenstein. All right, so this is a brief introduction of Gorenstein rings in the classical setting. It has its own limitations. We, in order to find properties of Gorenstein rings, even very, very basic properties of Gorenstein rings, we need the homological approach. Okay, so far I have been looking at quotients of regular local rings. That is a big limitation. We need to understand when general rings are Gorenstein. And so this approach, homological approach, is due to Hyman Bass. So for him, Gorenstein rings, a Noetherian local ring is Gorenstein, Noetherian local ring, Rm is Gorenstein. If I don't leave, its injective dimension is finite. Injective dimension of R is finite. Okay. So as I said, I will connect this definition with the classical definition, but we need to, we need to become familiar with the injective dimension. Yeah. So to detect injective dimension of modules, we will use the extension functors, and characterization of injective dimension was discussed by Professor Sengupta already in terms of vanishing of X. So I will just recall that, okay, before I start using. Right. So let me recall what is the meaning of injective resolution. Yeah. So this is a recollection of what is done already without proof. It is quite a while ago. So R is any ring. Injective modules are discussed even in non-commutative situation. So in homological algebra books, you will find left modules and non-commutative rings and injective resolutions. And so these are defined, but we focus on commutative rings. So R is a commutative ring and M is an R module. M is an R module. Okay. Then a complex of injective modules okay, is called injective resolution of an R module. It's called an injective resolution of an R module M. Okay. If if you look at the homology of this complex, let me call this complex by script I. I is 0 for all I bigger than equal to 1, and S0 of I is my module M. Okay, so if you insert the module, then we will get an exact sequence. That means this is an exact sequence. So we have the exact sequence of R modules where all these IIs are injective modules. Now this could be infinite, this could be finite. So as soon as you have a finite injective resolution, then we say M has finite injective dimension, and the injective dimension is defined just like the projective dimension. Injective dimension is the minimum of N, so that M has an injective resolution of length N. So length of a resolution is defined by the last index here. Okay. Suppose I have this injective resolution, there are n plus 1 injective modules in the exact sequence. Then we say length of this injective resolution is n. Okay. So if I have injective resolution of length n for M, then there could be other injective resolutions of shorter length. You look at the one which has smallest length, just like minimal resolutions of finitely generated modules or Lothian rings. Yeah. So injective dimension is the smallest of the lengths of minimal of injective resolutions of M. Okay. Yeah. So injective dimension could be finite or it could be infinite, and we will see that there are lots of situations where injective dimension is infinite, and Gorenstein rings capture the finiteness property of injective modules. I mean of when the injective module is finite. Okay, so this criterion you have learned already in Professor Sengupta's lectures. This is the characterization of injective dimension. This requires the ring to be Noetherian. R is Noetherian ring. But M could be any module, M and R module. Then the following are equivalent. One, injective dimension of M is bounded by N, then X n plus 1 R, okay, X n plus 1 R of N, M is 0 for all R modules N. And this can be sharpened by saying X n plus 1 R mod J, M is 0 for all ideals J of R. Okay, and if R is, so these three are equivalent. If R is Noetherian, then we can even sharpen the third statement. Okay. When R is Noetherian, I mean, sorry, when, just a minute. Yeah, sorry, this here, this Noetherian is not required. Okay. This is a very general criteria. R is any ring. Okay. When R is Noetherian, I can sharpen it. R is Noetherian, then J can be replaced by prime ideals in 3. So if I know that n plus first x of R mod P for every prime ideal of R, comma M is 0, then the injective dimension of the module is at most n. Okay. Yeah. So I will need another lemma, which I'm leaving as a small exercise for you. Okay. So this lemma says, in order to prove that certain X module is 0, what should you prove about the prime ideals? Okay. So for example, here in the third condition says that if I know which X module is 0 for R mod P comma M, then I know an upper bound on the injective dimension. Okay. So this lemma helps us in doing this. So let R be a Noetherian ring. Let R be a Noetherian ring, and n a finite R module, and M is any module, any R module. Okay, so R is Noetherian, base ring is Noetherian, N is finite module, M is any R module, and then if we know that nth text of R mod P, M is 0. Okay, for all P in the support of a finite module, okay, in the support of a finite module, then nth text of this module is 0. Okay. Very often we want to prove that certain x of nm is 0. Then to prove this, we will work with a filtration. Any finite module over a Noetherian ring, it can be filtered, okay, by submodules. It can be always be filtered by submodules so that the quotients are mod some prime ideals. And using this filtration, one can reduce the vanishing of nth text of n comma m to vanishing of nth text of R mod P comma m. So if we have the information about nth text vanishing of R mod P comma m for every P in the support of n, then nth text of nm is 0. Okay. This is, you just use the filtration of n and short exact sequences to prove this. I'll put it in the exercises. Okay, so keep that in mind to prove vanishing of certain x, nm. Yeah, another result. So that means vanishing of nth x of n comma m can be proved if I know nth x of r mod p comma m for various prime ideals, right? So this prime ideals are varying over the support of n, but support of n it can be an infinite set. Yeah. So how are you going to prove this for an infinite collection of prime ideals? So there we will use the following proposition to focus on vanishing of x n of r mod p comma n. Okay. So proposition. So we have a Noetherian local ring now rather than just a Noetherian ring. Rm is a Noetherian local ring. And M is a finite module. And P is a prime ideal different from maximal ideal. Okay. Yeah. So in this earlier lemma, we are faced with the problem of showing that nth x of r mod p comma m is 0. Yeah. So we focus on one prime ideal, which is not the maximal ideal. Yeah. And I want to prove that the nth x of r mod p m is vanishing. In order to prove this, we will prove the following result: n plus first x of r mod q m is 0 for all q belonging to variety of p and q is not equal to p. Yeah, that's the criterion. So in order to prove that the nth x of r mod p comma m is 0, I have to look at the prime ideals above p. Okay. But prove that the n plus first x of r mod q m is 0 for all q. So vanishing of n plus first x implies vanishing of nth x for a lower prime. Yeah. So this is a prime ideal which is not the maximal ideal. In order to prove nth x of r mod p comma m is 0, I have to see all the prime ideals. Yeah. All the prime ideals between m and p which are different from p and prove the same statement for n plus first x. Okay. Yeah, these are technical things, but you will see that to understand, to calculate injective dimension, we need all such computational tools about the X modules. Okay, so let us look at the proof. Proof is very easy. Okay, so vanishing or non-vanishing of X, we know very few tricks, and one of the tricks is the long exact sequence of X. Okay, for every short exact sequence, we have a long exact sequence. Now, P is not equal to M. Okay, if P is not equal to M, then when I look at R mod P, that is an integral domain, and M mod P is its maximal ideal. So therefore, I can pick an element X in M which is not in P, so that the multiplication map by X is an exact sequence on R mod P. It gives rise to this exact sequence. Yeah. Is this clear? Yeah, from n plus first x of r mod q comma m, I want to descend to nth x. Okay, and we have to relate the various xi's. They are related through by a long exact sequence. Okay, so if since m is not equal to p, I find this x which is in m not in p, and then this x bar is a non-zero divisor on r mod p. So I have this exact sequence, and this exact sequence gives rise to long exact sequence of the x modules. So I apply Hom R dash m. This is a contravariant functor. Okay. So this will give rise to this long exact sequence of x. Yeah. And I'm interested in understanding nth text of R mod p comma m. Okay. So go to that level. And so it will reverse this because it's a contravariant functor. Nth text of R mod p comma x m, okay, to nth text of R mod p m, okay, and then this map is still the multiplication map, okay, nth text of R mod p comma m, yeah, and then from here I go to n plus first level, x n plus 1 r mod p comma x m, etc. Okay, so this is the connecting homomorphism. Yeah, is this clear? Is this clear?
Yes.
Yeah.
Yes.
So now you see, um, what is the support of R mod px? Does it contain p? Support of R mod px?
No,
Yeah. Why is that?
because it is v of p comma x, and x is not inside p.
Right. So support will be a subset of primes which strictly contain p.
Yes.
Right. So this is contained in vp minus p. Right. Okay. But you see, the assumption says that n plus first text of R mod q m is 0 for all such q, okay. And the lemma which I left for you to prove is that whenever certain x is 0 for R mod q comma m for all q in the support, then the same x of n comma m is 0, okay. So this q is varying over all prime ideals which contain p comma x, and this is becoming 0. So therefore, it says that, what does it say? It says that nth text of this n plus first text of R mod p comma x m is 0. So now look at this long exact sequence. This module is 0. So what can you conclude from this long exact sequence now?
So multiplication by x is surjective. So
Yeah,
so x times n text will be equal to n text of R mod p comma.
right. But
And
then,
then by Nakayama we can say that.
right, very good. So n text of R mod p comma m is 0 by Nakayama lemma. That's what I wanted to show. Yeah. So vanishing is sort of descending. Yeah. I look at a prime ideal Q and I want to go below. Okay. I go below, then the index is reducing. Yeah. If I take a prime ideal which is strictly contained in Q, and then nth text of R mod p comma m is 0 if n plus first text of R mod q m is 0 for all q. Okay, this is it has to be true for all q not equal to p. But if p is just below the maximal ideal, what does this condition say? Yeah, if p is just below the maximal ideal, so as a corollary, if height of m mod p is 1, yeah, p is just below the maximal ideal, then this criterion says that x n plus 1 r k m equal to 0 implies x n r of r mod p m is 0. Yeah, do you see that it's a quick corollary of this earlier result, because in the support of R mod P, there is only one prime ideal which is different from P, which is the maximal ideal. Yeah. So how the vanishing of X is descending to lower primes. Okay. Yeah, the index keeps on decreasing as you go lower in the spectrum. Yeah, as far as vanishing is concerned. So this is very important lemma for various studies about Gorenstein rings. Now let us show that it gives me a formula for injective dimension. This is our first formula for injective dimension. And it has surprising consequences. Okay. So I have a finite module over a Newtonian local ring, finite R M K module. And suppose let M have finite injective dimension. Then injective dimension can be computed from vanishing of X, supremum of N, so that X N R K M is not 0. Okay. Yeah, when you have Newtonian local ring and a finitely generated module, M is a finite module, then how do we calculate the depth? By looking at the first non-vanishing X of K comma M. But to calculate the injective dimension, we have to see the last non-vanishing X. Yeah. So because injective dimension is finite, beyond certain stage, all the X are 0. In fact, if the injective dimension is N, then N plus first or N plus second, etc., all those X modules of N comma M will be 0. But it says that to calculate the injective dimension, I just look at the nth X of K comma M and find out the largest N, which is so that nth X of K comma M is not 0. Okay. Yeah. So if the depth is say depth is d, then the d text of K comma M is not 0. Okay. And the earlier X are 0. But this is if the injective dimension, suppose injective dimension is E, then eth X of K comma M is not 0. And if the depth of the module is d, then dth X of R Km is not equal to 0, but earlier ones are 0. Yeah. So there is always a non-vanishing X. There's always a non-vanishing X. Yeah. So for finite modules or local rings, and this D is the maximal M regular sequence in the maximal ideal. But there could be higher X which are not 0. So you keep on examining these X, yeah, and find out the one, the largest XE, so that XE Km is not equal to 0, then this E is the injective dimension. You might ask what is happening in the middle between these two non-vanishing X, and it's a deep theorem. You can read this, I can give you a reference, that the middle X are also not 0. We will not need this result, but you should be aware that there is a whole string of non-vanishing X, so that below these dth X, where d is the depth, there all the X modules are 0. And above the injective dimension, if the injective dimension is finite, all the x are 0. Okay, so all the non-vanishing x, they appear together. All right. Okay, so let us prove this characterization of injective dimension. Any questions? Any questions so far? Okay, so E, I said injective dimension is E. Suppose injective dimension of the module is E. Okay, then I want to prove that beyond E, all the X modules are 0 and each X is not equal to 0. Okay, right? So, yeah, sorry, not the injective. I want to prove this. Suppose E is the supremum. E is this right hand number. E is this right hand number. Okay, yeah. So that means each X of Km is not equal to 0. If E is the supremum of n, so that Xn R Km is not equal to 0, each X is not equal to 0, and therefore the injective dimension of M should be, yeah, what can you say about the injective dimension if each X is not 0?
Greater than.
It is at most E, right? Or bigger or equal to E. What is the statement?
Greater than equals to.
Greater than equal to E. Yeah. So injective dimension is greater because you will have if there is a finite injective resolution of certain length, then beyond that all the X are 0. But I have a non-vanishing X. I have a non-vanishing X, and so the injective dimension has to be bigger or equal to this T. Okay, so I have one inequality just from the definition of existence of a injective resolution, and so I need to prove the other inequality. So now prove the other inequality, that E is less equal to injective dimension. E is less equal to injective dimension. Yeah. So I need to prove that E plus first X, okay, of R mod P M is 0. Yeah, because we are in a Noetherian situation. If I prove this for E plus first X of R mod P for all prime ideals, then E will be less equal to injective dimension by that general criterion for detecting injective dimension for Noetherian when the base ring is Noetherian. Okay, yeah. So I have this Noetherian local ring. Here is my maximal ideal, and here is this prime ideal, and I'm looking for vanishing of this X of R mod P. Okay, yeah. But the previous corollary says how to descend. If I know n plus first X of K comma M, I just go below maximal ideal and I can conclude that nth X of R mod P comma M is 0. I want to conclude E plus first X of R mod P comma M is 0. But you see, each X is 0 and that is the largest one. And beyond that, all the X are 0. Yeah, beyond that, all the X are 0. So how are you going to prove this? So suppose this P was just below the maximal ideal. There was nothing here. Okay, there was nothing here. Then to prove that E plus first X of R mod P comma M is 0, I need to show that eth x of R, E plus first x, E plus second x of R of R mod M, M is 0, right? Do you agree? That if I have this, then E plus first x of R mod P comma M will be 0 if P is just below the maximal ideal. But E plus second x of R mod comma M is 0 because E was the supremo of N, so that nth x of K comma M is 0. So this is true, and therefore this is true. Yeah. So if P is way below, I have a chain of prime ideals, saturated chain of prime ideals. I can just go one step at a time below and conclude that x e plus 1 is 0. And I know that x e plus I r of km, this is 0 for all I bigger than equal to 1. Okay. So if I have to descend up to e plus 1, yeah, for some prime ideal which is deep below the maximal ideal, I can begin at the correct level of e plus I for suitable I, so that I can descend up to e plus 1. And that is allowed. Yeah, is this clear? Is this argument clear? This proves the other direction. Any doubt on this?
Yes, sir. Yes, clear.
Yeah. Okay. So one step at a time. We move from one x to next x when we descend from maximal ideal. But when we descend to a prime ideal below, the index of the x goes down. Yeah. As you descend below, the index of the x goes down as far as vanishing is concerned. All right. So that is our first formula. What good it is. Yeah. Who is going to calculate all these non-vanishing x? Okay. Yeah. So let us generalize this so that this formula becomes useful. We bring in another module. Okay. So this is the analog of Auslander-Buxbaum formula.
Hello?
Yes.
Sir, are we getting that at each step for every prime ideal R mod P comma M x is 0?
Yes. Below, see, if I have a chain of 3 prime ideals, yeah, P0 contained in P1 contained in maximal ideal, yeah,
Yes.
then in fact there are infinitely many maximal ideals between M and P0.
Yes.
There are infinitely many prime ideals between P0 and M. But what matters is how far below is this prime ideal. Okay, not infinitely many. So as soon as P is just below M, and that set can be an infinite set, okay, then I can conclude the vanishing of x e plus 1 R mod P comma M from x e plus 2 of R mod M comma M. Okay, but beyond E, all the x are vanishing of K comma M. Right? So if I have to descend to certain level, I can start with a very high vanishing x, right? And keep on descending up to a level that I want. That is what it is saying. It's a very formal argument, but it characterizes just as projective dimension is characterized in terms of non-vanishing of x, right? Projective dimension is characterized in terms of non-vanishing of Tor modules.
4K, yes.
Right. So this is the analog of for injective dimension. But the surprise is coming. Projective dimension of various modules can be all different, but the injective dimension will be unique number. So the people don't calculate injective dimension because it will turn out to be some constant, right? Some universal constant. Okay. Yeah. So that is possible by generalizing this result. Okay. But now let us have two modules. M and N are finite R modules, and Rm is a Newtonian local ring. Okay. And injective dimension of M is finite. Okay. So then depth of N plus supremum of I, so that x I R Nm is not equal to 0, will always add up to injective dimension of M. So that's the formula. Okay. So let me derive two quick corollaries before I prove the theorem. Yeah. Suppose in this, so this implies that that the depth of N is always less than equal to injective dimension of N, no matter which module you pick. If you have a finitely generated, if you have finitely generated module of finite injective dimension, then its injective dimension is an upper bound on depth of any other finite module. This is already surprising, right? N is just arbitrary finite R module. Then this, so this seems like some universal number, that it is a bound injective dimension of the module is a upper bound on depth of each and every finite R module. Okay, because the supremum of I is bigger than equal to 0, so depth of N is less equal to dimension, injective dimension of N. That is first corollary. Suppose I take N equal to R. Take N equal to R. If I take N equal to R, what happens to supremum of I so that x I Rm is non-zero? What is that number? How do I calculate X modules? The first module, x I of N comma M, the first module, I have to calculate a free resolution and then take apply the Hom functor into M and then calculate the homology. But if N is free R module, then all the X are 0, right? But M is a non-zero module. Hom R comma M is just isomorphic to M, that is not equal to 0. So supremum of I for N equal to R, this number is 0. And N is R, so it says that depth of R, yeah, depth of R is less equal to injective dimension. No, sorry. Equal to. Injective dimension is equal to depth of R, because this supremum of I is just 0. So isn't that surprising? Injective dimension of any module, if it has finite injective dimension of a local ring, is only one number, namely depth of R. It cannot assume. So it's a universal constant in the category of modules of finite injective dimension. Okay. Yeah. So then if you combine 1 and 2, it says that depth of any finitely generated R module is less equal to depth of R. If you have a finitely generated module of finite injective dimension, then depth of any module is at most depth of R. Okay, these are easy consequences of this. So let me prove the theorem. Okay, this is about all modules. Yeah, N. Let us look at, we are going to apply induction on the depth. Apply induction on depth of N. You see, if look at this third result. Third result says, you see, R is any arbitrary local ring. If R was a regular local ring, yeah, if R was a regular local ring, then this third result follows from Oscillander-Book's-Baum formula, right? Do you see that? Depth of n plus projective dimension of n is depth of R. Yeah, because for regular local ring, projective dimension of any finite module is finite. So for regular local rings, this third result is true. But here in this theorem, I'm not assuming that the ring is regular local. I'm just saying any arbitrary local ring, but I have a module of finite injective dimension. Now people realized later that this is a very strong condition. Having a finite module of finite injective dimension is a rather strong condition. So it was proved with a lot of effort that this condition implies that the ring is actually Cohen-Macaulay. Yeah, ring is at least actually Cohen-Macaulay. So this depth R becomes actually the dimension. Okay. Yeah. So we will apply induction on depth of n. So depth of n is 0. Let us start with depth of n is 0. If depth of n is 0, then the maximal ideal is associated prime of n, and therefore the residue field injects into n, and I take n mod k. Okay, so I have this exact sequence. So among the depth 0 modules, finite modules, the simplest one is n equal to k. Okay, let us first look at n equal to k. Look at n equal to k. And let us prove the formula for n equal to k. So for n equal to k, we need to prove depth of k is 0. Okay, and then supremum of n so that x n r n is k, km is not equal to 0 is injective dimension. But this we just proved in the earlier result. We proved this. So we know the theorem. So the formula is true. Formula is true for n equal to k. Yeah. Formula is true for n equal to k. If n is not equal to k, then let us look at this short exact sequence, which is coming from k containing n. Okay, k containing n. So 0 to k to n, and take the co-kernel n over k. Let's call it the co-kernel. Okay, that's an exact sequence. So now I apply Hom r dash m. This is contravariant functor. Left exact. So take the right derived functors of this, and E is the injective dimension. Suppose E is the injective dimension of M. Okay. Now the long exact sequence of X, I look at a part of this at the level E. This is a contravariant functor, so it is going to reverse this the modules in this exact sequence. So X K, yeah, X E R K M to X, okay, E plus 1, X T plus 1 Cm. Yeah. But you say E is the injective dimension of M. So what can you say about this X?
is 0.
That is 0, right? I have an injective resolution of length E. So beyond E, all the x of n comma m are 0. So this is 0 module. Okay, this is 0 module. So I have this x e n m mapping onto e text of k. Okay, is mapping onto e text of k. So that says that the because this is not 0, right? Because E is the injective dimension, and therefore this E text of NM is not 0. This is also not 0 because E text KM is a surjective image of E text of NM. Okay, and we know that E is the injective dimension. So X I R NM is 0 for all I bigger than or equal to E plus 1. And E text is not equal to 0. Okay, and that's what we wanted to prove because depth of n is 0. So injective dimension should be supremum of I so that X I NM is not equal to 0. And this we have proved when depth of n is 0. Is this clear? We have tackled the case when depth of n is 0. We are applying induction on depth of n. It was essential to do the case when n equal to k. From this argument you can see, okay, n equal to k case was done first, and then any depth 0 module. Yeah. Now assume that depth is positive. Assume that depth of n is positive. Okay. What can you do if depth of n is positive?
We can take question by some regular element.
Yeah. So pick an element in M so that X is n regular. And then I will relate X of n with X of n mod X. So we must take this exact sequence. It is almost obvious. We should look at this exact sequence n mod xn to 0. Yeah. And then consider the long exact sequence. So apply hom r dash m. This is contravariant functor. And so look at the ith. I want to understand the supremum of I so that x I nm is not equal to 0. And x I of n comma xn comma m is not equal to 0. Yeah. So I have to take the x at the ith level to understand the supremum non-vanishing x I. X I r nm to x I r nm to x I plus 1 and mod xn m to x I plus 1 r nm and so on. So I focus on these 4 modules in the long exact sequence. Yeah. So so suppose this module, yeah, this module, this is a problem. Yeah, suppose this module is 0. I plus first x of n comma xn. Okay, the depth, you see depth of n comma xn has reduced. This is equal to depth of n minus 1. So I know the result for n mod xn. Yeah, I know the result for n mod xn. So if this I plus first x of n mod xn m is 0, then this map is multiplication by x. So this will be surjective. Yeah. So again, ith x of n comma m will be 0. So if xi r n mod xn m is 0, xi plus 1, this implies by Nakayama lemma that xi and m is 0. Okay, so read the converse. If xi and m is not equal to 0, it implies xi plus 1 and mod xn m is also not 0. Yeah, so a non-vanishing x of nm gives me non-vanishing xi plus 1 of n mod xn m. Okay, and this says that if I calculate the supremum of I, so that x xi r nm is not equal to 0, and the supremum of I, so that xi plus 1 and mod xn m is not equal to 0. What is the relation between these two supremums?
First one plus 1 is
Yeah,
equals to the second one.
right. This plus 1 is equal to this because of this observation. Okay, because of this observation. So you see, this proves the formula because I know the result for n mod xn. N mod xn, result for n mod xn says depth of n mod xn plus supremum of I, so that xi r n mod xn m is not equal to 0 is equal to injective dimension of m. M is not changing. Yeah, m is not changing. But this is depth of n minus 1. So I absorb this minus 1 with this supremum, and then it will give me the formula. Is this clear? Yeah, we have proved a very important formula for injective dimension in terms of depth of arbitrary finite module, but everything is happening over a local ring, and there we have two arbitrary finite modules. Then the injective dimension of one module is related with the depth of another module. The modules can be arbitrary, you see. These two modules can be completely arbitrary. But the strong condition that is being imposed is that we have a finite module of finite injective dimension. Okay. Then depth of n plus this number supremum of I, so that xi n comma m is not equal to 0 will add up to injective dimension, and then it already implies that the injective dimension is the depth of R. If I take n equal to R, take n equal to R, then it says injective dimension of M is depth of R. Okay. So there is only one possible value of injective dimension, unlike projective dimension. Yeah. Any questions about this? Okay, so I have this number depth of R equal to injective dimension. Now let me prove a lower bound, that injective dimension cannot be too low. It is always bounded below by dimension of the module. So you have Noetherian local ring. And M, a finite R module of finite injective dimension. then dimension of M is bounded above by injective dimension. Okay. Let me derive a quick corollary. If Rm itself has finite injective dimension, then what it says, dimension of R is less equal to injective dimension of R, but injective dimension is depth of R. But we know that depth of R is less equal to dimension of R. So we have equality everywhere. That R is Cohn-Macaulay and injective dimension of R is precisely dimension of R. Okay. So Hyman-Bass definition of Gorenstein rings. For him, Gorenstein rings are rings of finite injective dimension, and says that in his definition, R is necessarily Cohn-Macaulay. Okay, and its injective dimension is dimension of R. So there is a minimal injective resolution whose length is dimension of R. So suppose dimension of R is D. It's a local ring of full dimension D, and it has finite injective dimension. Then this theorem says there is a minimal injective resolution of length D. So question is, what is the resolution? Minimal injective resolution, one can prove it is uniquely determined. Yeah. So we will not prove this theorem, but this is a beautiful theorem. It says that the minimal injective resolution is determined like this: R to direct sum of injective hull of R mod P, where height P is 0, then direct sum of injective hull of R mod P, where height P is 1, and so on. Finally, direct sum injective hull of R mod N to 0. Okay. Injective hull of an integral domain is a essential extension of that integral domain, which is also an injective module. Okay. So these are called injective hulls, and injective hulls exist. One can construct smallest one. You have seen the proof in Professor Sengupta's lecture that any module can be embedded inside an injective module in a sort of minimal way. Okay. And then once you have one injective module containing a module, then you can take the one which is an essential extension of this, and such module is called the injective hull of that module. So we take these domains R mod P for various prime ideals, take their injective hulls, and for height 0 prime, take their direct sum. This is an injective module. For Newtonian ring, direct sum of injective modules is an injective module. Okay. So, and then take all the height 1 primes and take injective hull of R mod P for height 1 primes and take their direct sum. That's an injective module. And this is an exact sequence. Okay. One is this. So this comes after many results about structure of injective modules and matchless duality. And so we simply don't have time. But you can read Brun-Serjov, where this is proved, or Matsumura also has a proof of this. Injective resolution of a Gorenstein ring of dimension D. That is the structure. Okay. So let me now show that the dimension of a finite module over a Newtonian local ring is bounded, it's a lower bound on the injective dimension. Yeah. So want to show proof. Dimension of M is less equal to injective dimension of M. This M is finite module over a Newtonian local ring. So suppose dimension is D. That means D is the dimension of the topological space, which is support of M. So inside the support, I have a saturated chain of prime ideals of length D, ending at the maximal ideal. Okay, and I want to show dimension of M is less equal to injective dimension. Okay, so take this minimal one. This is minimal prime in the support. So what do you know about minimal primes in the support?
Associated prime.
They are
Associated prime.
They are associated prime of the module. So that means R mod P0 injects into M, right? R mod P0 injects into M. So this P0 is also an associated prime if I localize and then go to this local ring, maximal ideal of this local ring. This is an associated prime of the localized module. Okay, and therefore the residue field injects into M localized at P0. The residue field at a prime ideal is denoted by Kp. So Kp0, okay, Kp0 injects into M localized at P0, and therefore the Hom Rp0 of Kp0 MP0 is not equal to 0. Yeah, that is not equal to 0. Now remember how the vanishing descends. If I know n plus first text R of R mod M equal to 0, that implies nth text of R mod P M is 0 if P is just below the maximal ideal. If height of MP is 1, then I have this statement. So look at the contrapositive statement. If this is not equal to 0, yeah, then this is not 0. N plus first text of R mod M is not equal to 0. So I have a non-maximal prime, and I know certain x of R mod that non-maximal prime comma M is not equal to 0. I can go above that prime and reach the maximal ideal. And I have a non-vanishing Hom. Hom is x to 0. So x0 of Kp0 and P0 is not equal to 0. Okay, and therefore I can rise up to d x by using this principle. Okay, so if you use this principle, that will say that because I have a chain of length d of prime ideals and Hom Kp0 M is not equal to 0. So it will say that x1 of Kp1 M is not equal to 0 and x2 of Kp2 of M is not equal to 0, and therefore dth x of R Km is not equal to 0. But injective dimension, remember, injective dimension of M is supremum of I, so that x I R K M is not equal to 0. I have found one non-vanishing x, and therefore this D is less equal to injective dimension. So dimension of a module is always a lower bound on the injective dimension. And injective dimension, we have proved it is depth of R. I can end with the definition. This is Hammond-Bass definition. R M Noetherian local is called Gorenstein if injective dimension of R is finite. Okay, and we have therefore already proved that Gorenstein rings are Cohn-Macaulay. Gorenstein ring is Cohn-Macaulay, and its injective dimension of R is dimension of 1. It has other properties. Localization of a localization of a Gorenstein ring is Gorenstein. You see, regular local rings were characterized first homologically by saying that all finite modules have finite projective dimension. Now we have a ring which has finite injective dimension. Okay, so it has a finite injective resolution, and localization of a injective module is an injective module over the localized ring. Okay, that's an easy exercise. I'll put it in the tutorial sheet. Yeah. So if I have a minimal injective, if I have an injective resolution of R and I can localize at a prime ideal, I get an injective resolution of the local ring. So Gorenstein property localizes. Yeah. RP will be Gorenstein. And similarly, if I go mod a non-zero divisor, then the Gorenstein property is preserved, and I can lift to R if the ring is local. Yeah, if R mod X is Gorenstein and R is local, then R will be Gorenstein. So I'll take up these properties next time, because I think my time is over, and I will prove these basic properties of Gorenstein rings, and then move on to the third definition, yeah, of due to Grothendieck in terms of the canonical module. But before that, I will prove the equivalence of the classical definition of North-Cotton Rees with this definition, that injective dimension of a local ring is finite, if and only if it is Cohn-Macaulay, and every system of parameters generates a irreducible ideal. So this I will prove next time. The proof will take half the class. Yeah, but these two definitions are equivalent, and that is nice to know. So we have a homological characterization of a ring which was defined classically, just like regular local rings were defined classically. Yeah, definition of regular local ring is quite simple, but people got stuck in proving that whether localization of a regular local ring is regular local. Yeah, but that was proved once there was a homological characterization of regular local rings. So nowadays, that is the trend. Singularity is defined homologically, so that it is easy to prove their properties and do computations with them. Okay, so we will stop here.